Good afternoon. Welcome to our Tech 101 webinar from the National Defense Industrial Association. I'm Mark Lewis, the Executive Director of the Emerging Technologies Institute at the National Defense Industrial Association. And let me begin by thanking all of our attendees for participating with us today and for your support of NDIA and the Emerging Technologies Institute. Especially thank you for joining us for today's webinar, which is on Digital Engineering 101. Presented by Jim Faist. This webinar is part of our Tech 101 series, where we try to distill complex technologies into introductory webinars with a focus on their national security impacts. Today's webinar is presented by AI Tech. You'll hear a little bit more about them at the beginning of the presentation, but we're very appreciative to them for their support of this webinar. As you gathered by the title, this webinar will focus on systems engineering. It should be a concept that I suspect is familiar to many of you. Especially, we mentioned a little bit in last month's webinar on Digital Engineering 101. So this is a very, very appropriate follow-on. Systems engineering is the field of engineering that basically includes the design, management, integration of complex systems. And I would argue historically, it's been the hallmark of U.S. engineering prowess, the fact that we have been able to successfully execute these large engineering systems. And we're going to be hearing more about that from Mr. Faist in just a few moments. Before we begin, a couple of administrative remarks before we all get started. First, all attendee lines are muted. If you have a question during the webinar, please submit your question in the question box in the webinar panel on the right side of your screen. We will do our best to get through all the questions during question and answer. No guarantees, but we'll certainly try. We are recording today's webinar. That's for members who are unable to attend, or for any member who's listening today and wishes to review the material at a later date. And in fact, in the next few days, we will post the recording, the slides, and answers to the question and answer session to our NDIA Connect for your review. Without further ado, let me introduce our speaker, Mr. Jim Faist. Jim is a recognized expert in advanced sensors, weapons, electronic warfare for space, air, and ground capabilities, with an extensive and distinguished career in industry and government in national defense. He's been recognized for progressive responsibilities and experience in military operations, advanced technologies, systems development, engineering leadership, program management. He's a member of the board of directors of Trident Systems Incorporated, member of the advisory board at Straddle Launch Systems Incorporated, and is a recipient of the Exceptional Public Service Award from the Office of the Secretary of Defense in 2021. Jim became the first Director of Defense Research and Engineering for Advanced Capabilities in 2018, and then I had the honor and the privilege of working with him on a daily basis, because I was the Director of Defense Research and Engineering for Modernization, although he certainly preceded me. And in that capacity, Jim reported directly to the Undersecretary of Defense for Research and Engineering within the Office of the Secretary of Defense until 2021. Jim directed an organization whose mission was set to recognize, explore, and force the development and integration of new technology to maintain U.S. technological superiority. And in that role, he was responsible for establishing a Department of Defense joint mission engineering capability, oversight of developmental testing and test facilities, as well as demonstration and validation of technology prototypes and rapid fielding activities. Jim served as the mission area advisor for warfighter portfolios in hypersonic, space, autonomy, network command control, communication architectures, and he also provided independent technical risk assessments of major acquisition programs. Upon leaving the department, Jim served as the vice president, chief technology officer for Lucent Government Solutions, where he worked on development of advanced 5G capabilities, artificial intelligence, electronic warfare, cyber, and communications. And now, without further ado, I will be turning the floor over to Jim, and I'm very much looking forward to his presentation. So, Jim, thank you for joining us, and the floor is yours.
Hello, Mark, and thank you very much for the opportunity to talk today, and thank you for the audience for participating. So I have a presentation I'll walk through today, and it really is to talk about where we are in system engineering, the importance of it, some good examples, and where we go to from here. So the focus is on, as Mark mentioned, System Engineering 101. The focus, because I like to talk about the hard problems and the opportunities we have. So we're going to talk about space as the example for system engineering today. So next chart. So I'm Certainly, I'm on the advisory board of AI Tech, and AI Tech is sponsoring this today. And really, AI Tech is a leader in mission critical terrestrial, air, space, surface, red hard, tolerant for space, digital electronic systems. And we're going to talk a little bit about where they are in different systems, both land, air, and sea, and embedded system development. And it's really the core infrastructure that's enabling a lot of the capabilities you see in AI today, for example. So next chart. Okay, we can skip this. This is my my bio. Go to the next chart. So as Mark mentioned, system engineering practice. So, from a layman's standpoint, general public standpoint, it's kind of a big word. What does it really mean? It really means the development of systems, and not just design development, but retirement of systems. And how do we maintain systems? So it's an integration of science, technology, management principles into building systems. So, some examples of systems we don't think about are the buildings most of us are in. Those are designed by engineers and architects. Bridges and tunnels we use all the time. Computers like we're using today are all developed by engineers. The automobiles we drive. I'm going to talk a little bit about satellites today. And how a system operates and succeeds is wholly dependent and determined by system engineers. So anytime you see a failure in something, it's a failure in system engineering, because it may be that it's not maintained or as things go along over time. So recent failures, they're in the news, just some general things. The Champlain Towers collapsed down in Miami, where you see about train derailments. And also NASA just had a recent rocket failure. The Astra rocket failed. Those are failures you see every day, and it's just how do you maintain system engineering quality throughout the life cycle of a system. Recent successes, on the other hand, the James Webb Telescope that just became operational in the last 12 months is truly a marvel. It's one of the greatest, most difficult accomplishments in space system engineering in our lifetime, and we're seeing the data from the universe now on a daily basis, just amazing. COVID vaccines are developed in the lab by scientists, but then engineers have to go ahead and figure out how we're going to get those out to the public, how we're going to manage and how we're going to expedite those expeditiously out to do it. That is the engineering process that does that. And in recent weeks, and actually in the last year, watching the Ukraine war with Russia, you read a lot about HIMARS. So HIMARS is a DoD example of something that was created by system engineers against really hard requirements, rapid fielding in this case to Ukraine, who really did not have knowledge of how to work HIMARS, rapidly learned that through good engineering interface and engineering support. And now we see the results on the battlefield for that one today. So those are quite different examples of system engineering, but just to set the stage on what system engineering is and how it relates to the public at large. So now we're going to focus on space system engineering and the challenges as the example. So go to the next chart. So, and you see about in the news, these rapidly proliferated constellations you read about. There's two commercial ones like SpaceX and another one that they're building lots of small satellites that are relatively expensive. And the idea is to provide high bandwidth internet services around the world, and to do that at a competitive price point. Well, the big supporting factor behind that makes it work is really the digital electronics that we're going to talk a little bit about today. If you think about what we've had for the most of our life, we've had a telecommunications infrastructure that's developed with the internet and basically Wi-Fi services that we have around the earth that we use in our phones, 5G, 6G, et cetera, that we get data and we use for video. Space hasn't been that way. Space architectures have not been that way. They've been individual satellites that communicated back and forth between the Earth. Data was collected at the Earth and then distributed across the land. Now with the ability to do microelectronics in space and do rapid iterations in low Earth orbiting satellites that don't have high life, but also low cost, now it looks like we can do a 4G, 5G network-based solution in space, and that will revolutionize how space is utilized both for civilian and military applications. At AI Tech, what they've done is their core strategy is they're predominantly a COTS, a commercial-based electronics firm, and they're using that successfully to migrate that capability rapidly into space. And that gives that Moore's law we talk about in engineering of rapid updates in processor horsepower. It also gives a cost point that makes these small satellites more expensive, less expensive, and are really the driver into making all this work in space systems. So that is really the excitement in space due to digital electronics revolutions. Next chart. So this is an eye chart a bit, but I just wanted to put out what a satellite is. And I think it's always, system engineering is the art of, how do you meet requirements and often opposing constraints, right? It's a very holistic, iterative discipline, and you have to make many different points from different engineering disciplines converge into a central design. So this is a pictorial from NASA. It's a typical satellite. Satellite architectures are evolutionary. They don't change a whole lot. The technology slowly changes over time. You get better solar arrays, you get better batteries like you read about in your car, lithium, et cetera, other things that are higher, have better energy storage. You get antennas that slightly change over time. The main thing that really changes now is the digital electronics boxes you see in here that really make it work and how it connects to the different pieces. So the system engineering on satellites is a combination of sensing communications people, like you might expect. Space is used for sensing and a lot for communication. Structural engineers that have to design these satellites, electrical engineers like myself, mechanism designers, power engineers. The interesting thing about space that I don't think people realize is you're designing something on the Earth with 1g gravity that has to operate in zero gravity. It also has to operate in a vacuum, which has its own constraints. So we think of our car that you drive down the road, everything stays cool because you're driving through air and you have fans and stuff to keep the systems cool. In space, you don't have anything like that. You have to use liquids and other ways to get heat out of a spacecraft. So there's a lot of unique things about spacecraft that you don't have on terrestrial air systems like an airplane. Next chart. So I put a functional diagram in here just to kind of capture the notes here. If I can get rid of that. This is a simple way to show how things work. I mentioned the fact that current satellites, they're highly dependent on ground stations for transmitting data up and transmitting data down, controlling the satellite. As we build a network layer of satellites at lower orbits that are smaller and inexpensive, and they network like we do in our cell phones, you won't need as many ground stations, right? To be able to communicate rapidly between each other. A lot of that's driven by the satellite ability to fly on its own. So there's an AI, artificial intelligence component on how we fly these spacecraft. And these are pictorial of the different aspects that we're going to talk about within a satellite. So you have a structure, the bus they call it, that houses everything. You have a power system, mechanisms that control things. You have to attitude and orbit control the satellite. Telemetry and command is fancy words for moving data back and forth from other satellites or the ground. Thermal management, I mentioned. Data. So, just like you have on your cell phone iterations, the data handling capability goes up. It used to be, I remember days when a megabit was a lot, then a gigabit was a lot. Now a terabit is not enough. We can store lots and lots of data. That allows video, like on our phones. It'll allow better video from satellite to satellite. And how do you transfer that back and forth? And then propulsion, you have to maintain orbit. When you're on orbit, they decay based on drag that you're on your orbit. And the only way to maintain that is through propulsion, to put the spacecraft in different places. And if you have many, many satellites to manage, and we're going to talk about that, then it gets more complex. Next chart. So the challenge is for space systems really is understanding the end mission that you're doing. So whether it's communications mission, and commercial, it's driven towards a market. Typically, satellite communications, like all the commercial ones, are typically that. Some sensing missions are emerging where people are providing different type of imagery, whether it's radar imagery or optical imagery, in a commercial thing that comes up with a business plan. For government needs, it's purely the missions like you read about today in the war in Ukraine, how you support the warfighter. You have to determine orbits, duration, budgets. It's gotten more complex in satellites because there's so many in low Earth orbit now and so many more going up. How do you keep them from colliding with each other? So space traffic management is coming into play, much like we have with the airlines. They're not populated, they're not with people, but you worry about commercial damage and physical damage of satellites. So it's getting more complex to manage that. And for system engineers, we read a lot about digital engineering. Digital engineering is the evolution of really models and sims and design tools merging into more system level constructs that you can better design and maintain satellites long term. Then what system engineers do for models is they develop the satellite specifications, the subsystem architecture, how you're going to test the satellite. A key feature that's evolved in the last 10 to 15 years, especially, has been on-orbit maintenance and uploads of capabilities. Things are more software-defined systems, whether they be communication systems that you need to change service capabilities or sensor capabilities. You can do more of that on orbit. And then system engineers, even though they typically own the technical baseline, they also have secondary responsibility to work with program people and budget people on budgets and schedules. So the real challenge too now is how, when you have 1,000 satellite constellations, how does this ever work as a system engineer, both short-term and long-term? And talk about that in the next couple of charts. So really the future is here, and it's all a bit of what I call AI tech's digital backbone that we've developed using COTS. These are examples of different units. You know, a digital backbone is a fancy word. You have a digital backbone in your car. You have a digital backbone in your aircraft. It really what connects all the systems that interface and work together as a system. So whether it be a processor on the edge, meaning you're interfacing with a camera on the right and you're taking images and you're digitizing them and doing signal processing on them. You have a network switch, which is no different than a network switch you might have in your house, a router it's called typically in an IT system. It has to route data smartly. It has an extra challenge on a satellite in that you're not just routing data within the satellite, but also satellite to satellite and satellite to ground, and then various processors for telemetry, how you control the satellite, how you work actuators and sensors. So it really is the core backbone on new satellites. And the challenge is, you know, how do you produce that at a price point that's affordable, that competes with your competitor's ability? So it's just like your iPhone, you know, you go from the iPhone 13 to 14, you're looking for new features. It's paramount that you do that on satellites now. And it has not been that way. Historically, satellite hardware, especially digital hardware, might be 10 years old by the time it ever launches off a satellite because of, you know, satellites that were really large might be in a higher orbit like geostationary orbits, which are very large satellites. You want it to be up there for 15 years. It takes an awful long time to design those. Instead of costing tens of millions, they might be in the billions of dollars. And the digital electronics baseline is very old by the time it gets there. And we'll talk about some other examples of that. Next chart. So people get a little confused on space systems because we always hear about the ones that cost too much and then others that, why are we building smaller satellites? You'll get that discussion. So I put it in two different options to group things. If you're building a few one-of-a-kind satellites for new or unknown missions, so what's an unknown mission? Well, we're going back to the moon. That's largely new technology for us. We're exploring Mars. We're doing deep space missions out to asteroids and further planets, and certainly national needs, national security needs. Those are really, in engineering terms, those demand a lot of technology investment and what you call invention and discovery to find solutions. So if you look at Cassini, which is the first one of the long-range deep space missions now is outside the solar system. James Webb, I mentioned, the Mars Explorers. System engineers supporting that are working very heavily with the scientific community, much more, because the scientific community is doing research on what the system needs to do while you're trying to come up with designs and go back and forth on trades to figure out what will work and what won't work. And that is that is a process, and it's really hard to define and manage cost and schedule when you're in those type of missions. So that in national security is system engineering, really supports dominant national security space capabilities. Same thing, but not quite as scientific in really defining and managing cost schedules and stuff like that. So those type of missions are the return of what you're doing far outweighs the risk and cost and schedule. And that is really one way to think about those type of space missions, that the return of what we hope to get out of those, whether it be national security capability or space exploration, really outweigh the cost. And then the end benefit always seems to be, as these systems get fielded, the feeling is, gee, that was so great, we need to do the next version of that to learn more new science. So those are unique. Now I'm going to switch gears completely. When you start building in system engineering terms, more than 6 of something is kind of a rule of thumb I've used. You start getting all the engineering unknowns out of a system. So think of like commercial satellites that do SATCOM, satellite communications, a lot of Earth observation stuff, and what we call proliferated low Earth orbiters, LEO type satellites, which are smaller and have much shorter duration lives. These things, whether they're ComSats or Earth observation satellites, system engineering really is focused on technical refresh, and we have a very good success usually on managing cost and schedule on those type of things. For a proliferated LEO, as the acronym is, it really is emerging capabilities with acceptable failures and attrition for small sats, rather than trying to make each satellite unattritable with over-design. We're not as worried about that. We're going to have, 1,000 of them, and we might lose 10 or 20 a year for different failures or reasons, but the cost is so attractive that we can keep buying more, and then we can upgrade those in the next 100 that we put up there. So the cost advantage of those really is so attractive, and then the capability migrates with it. So that's a natural for system engineering for good cost and schedule boundary control. Next chart. So what do we need in system engineering? What are the types of people that really are really competent, great engineers? And it really doesn't matter where they sit, whether on the government or end customer and industry, but it really is technically competent people that learn over time. Great system engineers do not start out as new grads. They typically are people that have 20 or more years of experience in engineering, different engineering disciplines, and migrate into the field. But they really need to be on the life of the program. How you maintain system engineering competency really determines end program success. And what may happen is you may have great system engineering during the research, development, and test phase of a new system, but how do you maintain that for 20 or 30 years if the system's going to be around that long? And then the best engineers always have high technical competence with tools and staff to understand the mission need. You have to have mission experts that are design development engineers for the mission that you're trying to do. I mentioned communications or sensing are 2 good examples. The other thing, system engineering does not work without authority and responsibility over the system baseline. And great system engineers attract great talent. Anytime I hear that companies have a really impossible time collecting talent, is talent in engineering, whether it's government or industry, goes to where they have the best engineering leadership and authority. So they go hand in hand. So when companies look about how great they want to be in system engineering, it's going to determine their business, if they're in the industry, and certainly in the government if they're trying to execute programs that they want to do. And there's a lot of discussion about small companies. So I started my career out in small companies, and in a small company on very complex system development, I worked on all aspects of that system. I could give you a story on every little piece of it. I worked right through fielding it, writing the test plans, doing all the development testing, doing the integration, doing all the operational testing, acceptance. They have a big advantage over a lot of times the larger firms where engineers might get stuck into a into one specific area. You think, well, I'm a digital engineer, I'm going to be doing FPGA development for the rest of my career and I can't get out of it. So you really have to, as an engineer, if you have the interest in being a system engineer, you have to reach out and be willing to take personal career risks that you're going to, hey, move up and try different things. You may want to focus on software. You may want to do more analysis work on engineering projects. And that's the way that's why you become a really great system engineer in our field. Next chart. So initiatives in DoD system engineering. As Mark mentioned, I went into the Pentagon after really a career in industry as a chief engineer and executive in different types of development roles. And one of the groups I had was the engineering arm of OSD. And we had a broad role. We had a role for policy, as Mark mentioned, independent assessment. What was lacking too when I went in the Pentagon is, especially with the rise in the threats that we face today, we needed to revitalize a couple things. We need to revitalize system engineering, called it mission engineering, within OSD, working with the joint staff to really bring in technically competent people to work with the joint staff on evaluating architectures for the future warfighting concept. And part of that then also was, how do we improve the DoD instructions on engineering? What I found as an engineer, and I'll give you a certain thing that's kind of interesting, I think, especially if you're an industry engineer. I don't think as an industry engineer, I never heard of or used the 5000 instruction, right? The 5000 instruction, when I finally read it as I came into OSD, it really just documents good engineering practice that all of us that are practicing engineers have lived since undergrad school, how you work in companies, how engineering processes work in a corporation, which are the same whether it's government or commercial. And that's what we use. But I did have the opportunity to look at the 5000 instruction and look at improving it. One thing that was glaring is that OSD in its traditional role or recent role is driven too much by program management role. In an engineering development company, they're equally balanced between the chief engineer. Chief engineers don't report to the program manager in development private practice companies. So we define the chief engineering role within the 5000 in an attempt to give them more authority on DoD acquisition programs. The other thing is system engineering plans. A system engineering plan in engineering is DoD's word for, people call it an A-level spec on a system or something like that, which really defines the system you're building, why you're building it, how you're going to do it, and how you're going to test it, right? So that is a classic engineering document, whether it's commercial or government. And I think that was certainly an area that I saw lack of attention to on the major acquisition programs. And you can see it when the program got into specific troubles and issues, you look at it and say, gee, why did we assume something is already developed and is mature at the level required to start the acquisition program, when really it's still a lab drawing that probably won't work based on simple analysis. So this is an area too, I think, is something that people need to do. We also put out a system engineering guidebook. We had a great team in the Pentagon, brought in some industry folks, and that was also a good thing to do. Other things that are missing in DoD engineering is we really need an exchange program. We need an exchange program that, and I understand the OCI issues and many of the legal barriers we put up, but the best system engineers to architect and design and build DoD systems on the government side are people with very strong industry experience. And those are good talent to move into as an exchange into DoD programs. So that's really all I have for today. I want to mention the CERC2, which is a good center that we supported that really helps with engineering, the practice of system engineering and supporting conferences. And with that, I will open up for questions. Thank you very much.
Jim, thank you so much for that. We've already got questions pouring in, so I will go down them in order and see how far we get through. So start off with a question from one of our attendees and asks, how do systems engineers deal with human-machine interfaces, including potentially cognitive overload issues?
So good question. I mean, even the earliest system I did, the first system I ever did, human machine interface is a big deal. What you have to do is you need two groups of people when you're doing an interface. If you're replacing a legacy system, typically the person from the legacy system wants the new system to work exactly and look like exactly like the new system that you want. And sometimes, most times that doesn't work. If you're trying to automate something, automate functions, it can be a barrier to innovation. So you need the technologist on advanced human machine interface work with the operators to come up with that basic design. And it's very important to get that up front, because the last thing you want to do is have to change a processor architecture or display architecture because you haven't settled that argument about how many screens you're going to have and what that's going to be. When we get to AI type systems, where less and less interface on the operator, that's also a discussion. You have to set, AI will drive capabilities you might not want to have based on policy. So you have to solve first what the technology can do, and then you have to bring the policy people and say, okay, what are this you don't like? For example, the AI topic about autonomous weapons, right? And people are afraid we're going to have tanks that are autonomous. Well, we are building tanks that are unmanned. How autonomous they operate will be up for discussion. But we've been using autonomous air-to-air missiles for 30 years. Launch and leave, it's called, right? We have plenty of other weapons that are like that. So when you talk the DoD realm, you have to balance capability and lethality against our adversary and not limit yourself, right? So when you talk about the DoD mission. And then when you talk about autonomous cars, what we're finding is they ain't perfect, right? They have errors and they are going to cause accidents like we're seeing. What's an acceptable accident level and what's the liability on the manufacturer is probably, in that case, is going to determine how well they're adopted.
Yeah, very good. Next question. Our audience member is asking, what are the key issues vis-a-vis digital modeling and validation for the system engineering field?
Yeah. So the biggest barrier to get over in digital models, so if you got a complex system, you're going to have many providers. Each one has their own intellectual property within the product or capability they're selling into that system. How do you make that work, right? Because typically, if you're a small company and you have a model on your product, you're probably not going to give that to the system integrator, right? So you have to set up that first, and then the interfaces, you have to have a common, like on the satellite, you have a common framework, on how the system communicates. It's published standard interfaces. People know how to plug into your digital backbone pretty easily, and they can operate and write their code to it. Those are all the issues. And then how do you maintain that? If you're the government, when you have a slew of providers and you have a system integrator, what's the government's approach for sustainment and maintenance that's economical? And how you manage that, right? That is a really tough problem for digital engineering.
Absolutely. And ties in very well with, as you know, our previous seminar was on digital engineering. So a great tie-in question. Here's a question. Individual is asking, how can the DoD leverage systems engineering principles to help counteract vendor lock?
Good question. It's we've all struggled with that. It's very hard. It's not impossible, but it's hard to change suppliers with a prime, especially on a legacy system. It's a lot longer process than most companies are willing to do. I've been successful doing it, but it takes a lot longer and a lot more effort to break onto a system as a supplier than if you were with the supplier and competed up front when they won the initial program. So it takes a lot more energy than people want. As far as technical refresh, it gets down to the government system engineering authorities on the systems they're buying and how they set up the sustainment up front on how they're going to sustain the system, because they have to set up the intellectual property rules. They have to set up who's going to own the development, sustainment workstations, what data the contractor is going to provide that can be picked up by others. So it's a lot of it's on the government side, and I haven't seen a lot of talk on that. It's very hard for the government at this stage to implement that on, especially the larger systems. It's much easier to do when it's just a R&D or a technology development program, not so easy on a program of record.
Very good. Oh, here's a funny question. So the Webb telescope has produced incredible results, but it did fall behind on cost and schedule. Way behind, by the way. It was
Oh yeah. That's
way behind.
Yeah.
Yeah. What did we learn from a systems engineering perspective that might remedy this in future state-of-the-art projects?
So the two hardest problems on the James Webb, in my view, because I've seen it a bunch of times. First thing, it was the first time we're putting a telescope close to the sun, right? It's way out there and it's very close to the sun. So you had a massive problem. You have a telescope that's looking in the IR domain that can't stand solar interference to see the image, right? So how you're going to shield that telescope from the sun took years to figure out how to do it. And it's very, very complex, very complex. And the second part is the mirror itself, on how we learned through the Hubble and other things that when you put that type of mirror, which is a panel-based thing on orbit, the tolerance you need is so precise on how you do that. That took a lot of discovery as well. So, you know, what we learned on the Hubble is, and it's not NASA's fault, it's really just when you define a science mission, you need to invest a lot more resources on those hard problems before you start the system build, right? And you could look at DoD, you know, with the tanker, the new KC-46, they wanted to build a remote vision system on the tanker. That should have been developed as a low TRL science project that grew over time, and you experimented with it and got it to a mature level before you did it. So you'll pay the price there on the end. You pay the price on James Webb. You know.
So if I can ask, so is that a systems engineering failure or an acquisition failure, or both?
Well, I think it's how you define the acquisition process, right? So if you have a mission need, you need a rigorous science, you know, technology development program bounded with certain goals to prove the technologies that matter. In your area market's hypersonics, right?
Yeah.
And when you feel this is the system part, so the system engineers have to say, okay, we're far enough along that we're ready to build a prototype full system. And then you need to build a prototype, and the prototype needs to be exercised against as much as you can afford of the mission threads that you want to do. We couldn't build a prototype James Webb, right, and put it out by the sun. That would have been enormously expensive. So we're taking a lot of risk with James Webb, and system engineers have to communicate the risk on what you're developing accurately. You know, I thought in the Pentagon, you know, and you know it, they did a really good job estimating based on previous things about what systems were going to cost, which was fine. But it's averaging a lot of risk programs to come up with a number versus, okay, now where would you want to take a risk is really the question, right? And that's the hard thing, because when you take risks, as we know on the hard programs, you know, you're not going to get 100%. You're going to get 70, 80%. And then, okay, now what do you do next, right? To try to get to an end capability. But you have to do that in DoD because the threat is doing the same thing. They are an intense competitor, right? And you have to stay with them on the science technology side.
Yeah, no, absolutely. Here's a question from one of our listeners asking, how does a system engineering team determine the financial cost benefit ratio for any particular possible technical change or improvement in a complex defense system?
Well, you know, my view has been when you had the team, you know, a system engineering team is usually pretty big, right? You have all aspects of a system. You know, you have the test component, you have the science component, you have a science team on a system engineering team. You have a lot of people call them project engineers who really work to help build a project plan and estimate of cost and stuff like that. And when you have all those elements on a system engineering team, we're usually pretty good at estimating costs. I mean, it depends on your knowledge, but when you have a certain level of knowledge using the normal system engineering process, I would put out that most really competent system engineering teams can hit a cost within 5%. Now, the issue has always been when they come up with the cost within 5%, it could be way more than anybody wants to spend on it, right? And then you get the circle, right? Which is, okay, we're going to throw something out. We need to scale back what we're doing. And then it gets into the risk areas. We're going to take more risk to say we're going to save cost, and maybe that doesn't work out. So it always, and digital engineering is a help, right? If you have a digital model that's more defensible on the mission side, so if you change a parameter here, say on an antenna on a spacecraft, and it saves you $10 million, how does that impact mission performance? So that cuts service by 5%, which means it cuts the revenue by 10% that you're getting. That's what digital engineering is going to do. So we'll put the system models in with the financial models to tell you impacts, right? And then you can do the trades, right?
Yeah.
That's what it is. And, it's kind of like the nice thing about the LEOs is you can take those 80%, 70% satellites and put them up there because they're not that expensive. And then the next iteration, you can better economically produce, more capability, and then the revenue guys and the commercial guys, is that making enough revenue that, that works, So.
Yeah. So speaking of LEO, I'm going to jump to the next question. Our participant asks, in terms of sustainment, has there been a pivot in planning for total life cycle sustainment and costs with the eventual development and fielding of returnable or reusable satellites? So I guess they're looking at satellites that we bring back.
Yeah.
Similar to Falcon X, the Falcon's SpaceX reusable capability. And the person continues, it seems like a huge mindset change in that if successful, we won't be assuming future satellites will ultimately just become space junk, in quotes, at the end of their useful life.
Yeah. So satellites, by rules, and I'm not the pro on it, but my understanding is when you launch a satellite today, either it's planned, it's going to come back in the atmosphere, or it goes into a parking orbit when it's end of life. Those are basically the two things you do with a satellite. Recoverable satellites would be difficult too. I'm not sure that really, what would you recover off a satellite?
Yeah.
That would be useful. It wouldn't be the solar panels. You could say, the bus, but you could get a few parts of it. I don't think economically it would work. I mean, the big cost advantage, if you're getting satellites down to $10 million or $20 million a piece, you can buy a heck of a lot of those. And if you can launch them up at 50 or 60 each launch, that's you can put up a whole constellation doing a mission with one launch, right? Versus a big GEO bird or a MEO bird that's going to be $1 billion or $2 billion, right? And now they may last 10 or 15 years, but the capability atrophies over those 10 to 15 years. Whereas with these, you can just put up another 50 or 60 of them. I think the biggest question is going to be the space traffic management, because they say we get tens and tens of thousands of these LEO satellites up there from many different companies and countries providing sensing and communications, all these good services, both for security reasons and commercial, is you are going to have collisions. You are going to have damage. You're going to get more damage to these satellites. It will be interesting to see how it works out over time. It's a big place, though. Space is a big place. So, and LEO's a decent sized place.
Yeah, no, absolutely. Here's a question. I think I know how you're going to answer this one, but I'm going to pose it anyway. So individual is asking, is it commercial off-the-shelf COTS or standardization of interfaces across subsystems that ultimately enables rapid innovation and deployment?
I think we're pretty much there on standardization of interfaces. I think the market has driven all the suppliers to that. The COTS solution at AI Tech is cool because their predominant business has been the military aero environment, so airplanes, ground systems, and they're pushing state of the art. But when you're doing ruggedized mil platforms, aircraft and stuff like that, you're building to a higher engineering standard than other things might be, and the ruggedness is there. So you have to do testing. So it's actually very affordable suddenly that you couldn't do in GEO or MEO, where I can get 100 parts, commercial parts in, and I can radiation test the lot, and I can find the number that are worthwhile and will work in a LEO 2 to 4 or 5 year mission confidently. And suddenly it's a dramatically cheaper part that you can use for that. So that's how commercial is used. You have to upscreen commercial parts against rigorous standards, depending upon the radiation levels you're targeting, whether it's 100K rad or 25K rad. And that's what you use in your design, and that's how you build your system. So that's what's so exciting about the LEO market. So suddenly now I'm using much closer to state-of-the-art digital processors I can use for everything. So, and it's the same old thing, right? Just like your iPhone, everything is smaller and smaller. I can pack more and more horsepower in each satellite that I couldn't.
Yeah, absolutely, absolutely. Is this where we get to tip our hat to our friends over at the Space Development Agency, Derek Turnier, and the great work they're doing on Proliferated LEO?
Yeah, they got to get it up there and it has to work. And the real question with SDA is, how is the network going to work? You have multiple providers with multiple controls of spacecraft. The last thing we want for that architecture is a government centralized ground station. It's a big target, right? So
Right.
How does the network work that gets you away from ground stations and gives you the data connectivity within the network, right? So really what you need is kind of like a, commercial, commercial like a Verizon or somebody like that really works network architectures and network flow. How that's really going to work in space is probably critical and interesting, because that's going to change everything on what we do on the DoD side for SATCOM. Because, the physics from LEO on comm signals is dramatically better than MEO or GEO or any other place, right?
Right. 1/r² works in your favor, doesn't it?
Oh, it does. It does.
Yeah. Absolutely. So here's a question that switches gears a little bit, still in the space domain, but switching gears a little bit, which is, how can we improve the microelectronics qualifications process for systems that have to be designed against for space hardening?
Yeah, it's there's two big, I think there's some bottlenecks you always have in space, from my experience, which is companies need to develop really strong relationships with radiation test facilities. Typically, companies don't have those in-house. They go to various places in the country. It's kind of like your wind tunnel problem, Mark. It's how many wind tunnels you have. It limits hypersonic development. Radiation test capability is critical. It's absolutely critical. And I think the market is still learning how to do it for the high volume LEOs, how we're going to do that and what are the levels of testing that we're going to do? Because, how it works in space is you don't consider something mission ready, complete, fully qualified for space till it actually flies in space. So we don't have a lab up there you can go throw your product on in LEO easily to do that. I mean, you can put it on CubeSats, people do that. Those are short duration missions. You really want to hook it up into a network and do that. Years ago, I had a project where I put a project on the space station, and that worked pretty good. We put it up there for a number of years, and it really fleshed out things we didn't know, right? Because when you get into space, it's radiation degradation on electronics, but mostly what happens is you get upsets. It's kind of like, not fading like you have on your cell phone, but you just have data dropouts, and they can destroy your comm signal in radiation. So how do you do that? How do you recover is a big part of it. There are plenty of engineering standards. NASA's very good at that. Some of the other Space Force, others have development things the classified guys do on how to test space systems, but it's not at the volume that we're talking about. That's the challenge.
Right. So here's an interesting question coming from one of our audience members, which is, can you compare and contrast systems engineering within a single company compared to how it's practiced between multiple companies?
I've had the advantage that I've worked in quite a few development companies, and all of them, like I mentioned earlier, the practice is the same. The question is going to be, in any company, the authorities and the strength of the engineering organization determines its success. So I worked in a small company when I first started, and they had a matrix, and we had about 100 folks, and the chief engineer, VP of engineering, was a national treasure, right? We all worked for him, and he had authority to sign things off. Sometimes you go to the big companies, especially, that gets abrogated. Same thing in the government. It gets abrogated by program business people at times, in which case it's not too effective, right? Because engineering, whether it's in OSD, needs to be one integrated group of people, right? And system engineering works hand in hand with all the disciplines. So, most engineering comes, you'll have mechanical department, electrical department, right. You'll have a science group, you'll have different groups. They all work together but they're led by the system engineering person, not the program people or other people. That is really key. So I haven't seen the successful development companies do that. I mean, that's very obvious when you see it, and it's training and how you do it. Some companies are phenomenal at doing engineering training and development and system engineering. Some are not. The annotation of a system engineer has had the problem when it started out is a auditing function, I would call it, right? People that ran various tools, there's new tools out today, and those are good things, right? You want to audit a design, you want to maintain the technical baseline, how things connect and how they flow. But that's more the technician side of system engineering than the architecture and the science side and the testing side. They're all important. But that's the other thing that's kind of been a real problem, and especially the larger companies, that a system engineer has a connotation of an auditor type function. Yep.
Yeah, absolutely. So that's a good lead into, you mentioned at the top of the webinar that, of course, you had set up the mission engineering office in your organization. And so the question is, what is the difference between mission engineering and systems engineering?
So mission engineering is just the top level part of system engineering, right? Which is, okay, we have, in this case, threats to the country, right? And mission engineering looks at how we're going to do the mission today versus how we're going to insert new technologies and new capabilities to see how that changes the mission, right? So you read about wargaming and stuff like that. Mission engineering is the engineering arm that helps you try out different concepts and techniques in that case in DoD in a war game to see, okay, if you develop this new capability, hypersonics, how well is it going to work? How it's not going to work, stuff like that. Where are the hard problems you have to solve? A lot of what you read about in DoD, it used to be called fully network command and control communications. Then they came up with the buzzword JADC2, joint all domain command and control communications. It didn't take a genius to figure out as an engineer that the comm network and how well it works across the services in DoD and our allies is really the critical function you have to make sure you get right. And that's going to determine success, right? So mission engineering is doing that. Next level down are people doing system architectures on specific areas, right? Whether it be hypersonic weapons or, sensors or whatever else we're working on.
Yeah, absolutely. Absolutely. We've got a two-part question, and it goes as follows. To what extent is the Department of Defense requiring the use of model-based systems engineering as foundational to systems engineering? So that's part one. And then part two is, where do you think DoD and the contractors are in terms of adopting MBSE, model-based systems engineering?
So if you're talking about at the supplier side of things, right? So you're in a system, pick your thing, an airplane or something like that, and you're talking the avionics suite or the engine, the people that supply those do great. Their business is driving them to model-based system engineering tools on what their products are, because it saves them time and money and staffing and everything to help develop products, maintain products. AI tech is big in that area to build those systems. When you integrate them all together, you have all the problems of how do you integrate that into a digital twin of a complex system. Then you get into the first question is, what is the model of the system? What are you trying to get out of it, right? Because that determines the fidelity, right? And that it's like if I build an airplane and it has all these antennas on it. I mean, there's a lot of ways to model an antenna. And if you do, what level are you going to do it? And it's going to get more complex based on how accurate you want the physics of the antenna to be represented in the model, right? So there's a lot of buzzwords around MBSE, but you really have to ask yourself what the intent is. So on the government side, I think we're struggling, and I've asked the question a bunch of times, are digital engineering requirements and MBSE requirements showing up in requests for proposals on systems? And it's a hit or miss. Mostly it's no. I mean, there are examples where, and we funded some of those, Mark, when we were in the building, and it's an expense, right? Because it's a big expense to build an MBSE model on a system, because it's an upfront expense that if you maintain it, saves you a lot of money downstream, but it costs you money in the development phase, right? So I think we're still stuck in that for most things in the department, really doing that it could stand independent engineering assessment, whether it's going to work and be effective. I think we're a long way from that, in DoD. Now other groups, NASA, I would say NASA does a pretty good job of that, right? Because NASA has a much bigger, relatively sized engineering workforce in the government, from a relative standpoint than the contractors do typically. So they do a pretty good job on, depends on which group, but really maintaining MVSE models. Like JPL does an extremely good job of MVSE because they have to plan these big missions that go on for decades and decades, right? And test people's careers. Yep.
Yeah, no, absolutely. Here's a question about how can systems engineering principles and practices be used to optimize team performance? And the questioner goes on to say, are requirements to optimize team performance allocated to hardware and software systems beyond the traditional communication interface principles?
So he's trying to use MBSC to optimize staffing.
Well, just systems engineering principles in general. Can they be used to optimize team performance?
Yeah, I learned, and I won't say where, but early engineering training, and some of it's taking the rough edges off of all of us, because working in an engineering team of many different types of people with different backgrounds to accomplish something is a hard thing, right? So you have to, what I've seen that was really effective is the team building of the engineering competence and working together has to be sound, right? And that means some tough problems at times. Not everybody wants to be in those complex teams doing the work. So the system engineer, part of that is personnel, right? The project engineer typically is the one that manages personnel, and it's matching people. Sometimes it's human beings aren't fitting one team and you have to put somebody else in there. So no matter what you do, you have to have the flexibility to move people in and out. Now, the good thing about engineering, if you're in development, typically you're not working one project. If you're an engineer in a particular company, you might have 5 or 6 different projects, and you pretty much find your own job, right? And that's the accountability that's put on you as an engineer, that you will be, if you perform well on teams and you do great work, whether it's hardware, software, whatever you do, testing, you will be in more demand than you can handle. And so the market does work that way, especially in the private sector, that your performance and how you interface with people is being held accountable, right?
Yeah, no, absolutely. And Jim, I'm going to make that the last word because we are at the top of the hour. So first, a profound and profuse thank you for this. I've enjoyed this webinar and enjoyed hearing your thoughts. And the long list of questions we've gotten shows that the audience has been very responsive as well. Let me thank all of our audience members for their attendance. Thank you for your great questions. We will post the recording online as soon as possible. And as always, if you have feedback about the Tech 101 series, especially topics you'd like us to cover in the future, please email us at eti@ndia.org. If you allow me, I want to highlight a couple of upcoming events. We've got several webinars in the works. The next Tech 101 will be on nuclear fusion, and that is going to be on March 28th. You'll hear about the real science and maybe some of the hype associated with nuclear fusion, especially in light of recent announcements. April 20th, we'll have a Tech 101 on 5G communications. Also coming up, April 13th, we will have an FY24 S&T budget priority rollout. That should be with the Undersecretary of Defense for Research and Engineering and leads from each of the services, talking about their priorities and how they formulated their budgets. And then on May 2nd, the Defense Technical Information Center, DTIC, will have a webinar in which they talk about their role and their work with the Defense Industrial Base. And finally, before you all go, I want to remind you that ETI is going to be hosting our first annual Emerging Technologies Conference. It'll be at the JW Marriott Hotel in Washington, D.C., August 28th to 30th, 2023. And please join us. It should be the Emerging Technologies for Defense event of the year, maybe the decade. And with that, let me thank you all once again for your participation. Have a good rest of your day.